Hi everyone, I am back solving Advent of Code 2025 day 9. Um, cool. So the description today was really short, so I don't really have to skip anything, but let's see. So it says here, some of the tiles are red. The elves would like to find the largest rectangle that uses red tiles for 2 of its opposite corners. I see, okay. Okay, cool. Yeah, okay, cool. This makes sense. We just find the maximum size. Okay. I think this is pretty straightforward today. So you have the, I'll just call this as x and y. R and C is equals to for v in sorry, what is it called? Red tiles. R and C. List of RC coordinates. Okay. I guess what we want to do is the n squared solution is very straightforward. Basically, for every in the range of n, j in the range. Oops. Oh, maybe let me increase the font size for you guys. For j in the range, j in the range of everything after n. So we don't want to have any kind of intersecting pairs. We then want to find the height and the width. So the width is the absolute between the data of I at the width is the column, sorry. So the width minus the data of j of 1. Height is the absolute of the data of I of 0 minus the data of j of 0. Then we have the answer is the max of the answer, width times height. Let's see. Uh, 36. Ultimately, the largest rectangle you can use is this. Oops, this was not it. 5? Yeah. How come? No, why is this the case? Oh, I guess you include yourself? Oh yeah, okay, cool. I have a strong suspicion this does not work once we brute force it, but I guess we'll find out. Oh, it worked perfectly fine. Cool. The second bit is you can turn tiles from red to green, so rectangles can only include red or green tiles. The red tile, every red tile is connected to the red tile before and after in a straight line of green tiles. And then the list wraps, so the first red tile is also connected to the last red tile. And so all the tiles inside of the red is also green. The remaining tiles are neither red nor green. So the rectangle you've chosen must have red tiles on the opposite corners, but any other tile must be red now, red or green. Wait, what? In your list, every red tile is connected to the red tile before and after it in the straight line. Oh, I see, okay. I see. Okay. So we sort of have a stricter bounding box on it. Cool. So I don't think it's particularly related to the first bit anyways, so we can kind of ignore it. the first thing I want to do is retrieve the data for the RC coordinates, and then we just need to form find out the green tiles and form the green tiles. So how would this look? Well, the coordinates would be in, I guess, clockwise order. And so we need to basically judge to determine where the lines are drawn. Yeah. Yeah. Before and after it. So I'm assuming here in this case, the list is given in the correct order already. So it's probably not necessary to over-engineer this. But basically, we want to say that the green tiles is the set of RC coordinates. Sorry, it's the set of RC coordinates. And then yeah. So we basically just want to take you and your partner, and then we eventually loop backwards as well. So it would be for every AB in the zip of the red of the data, with the data 1 onwards, but I loop over to 0. Let's just print out A and B, just to be sure what these are. Let's see. Oh, oops. Yep, and then yeah, so you can see 7 to 1. So this would be. Wait, hold on. 7 is 0, 1, 2. 3, 0, 1, 2, 3, 4, 5, 6, 7. Ooh, what? 0, 1, 2, 3, 4, 5, 6, 7. And then 2. Oh, this doesn't seem right. 11 and 1. How is 11 and 1 like this? Hold on. Very lost right now. Oh, okay. I'm assuming it's padded. So 7 and 1. 0, 1, 2, 3, 4, 5, 6, 7. Oh, no. What? Okay. No. So 7 and 1 is this one. So it's, I think it's assuming it starts with the bottom left or something. Yeah, I think it doesn't really matter in this case, as long as we know what those are. So we are now spanning the green tiles. So we have the okay, this is a bit strange though. Yeah, and then yeah, okay, that is weird, to say the least. Wait, hold on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This does not even make sense. This literally does not make sense, man. Yeah, like, okay, so you say 2, 5. Where is the 2? 2 is 0, 1, 2. So 2 is the column, so it's the x coordinate. 0, 1, 2, 3. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then 0, 1, 2, 3, 4, 5. Okay, so it is xy coordinates, which still doesn't really solve the problem, right? Because how did you get so many more coordinates than normal? Okay, I think I know why. Yeah, so it's, this is actually x. yeah. You know, but I am interested in doing for every y and then for every x. No, wait, hold on. This actually does not make sense to me. This is y. This is x. So for every row, we go every column. Still wrong. What is? Hold on. I'm so confused right now. For the max x and the max y. Okay. Alright, I am back. I basically just went to take a nap because I was really tired today. But before I was napping, I was also thinking a little bit about the problem. But yeah, essentially, I was in the middle of solving, like looking at part 2. I was trying to visualize it. And I have come to the realization of two things. The coordinates given is by x and y, so it's actually given column and then row, not row and column. And the grid size is the maximum plus 1 because it's a 0 index. So this is how you actually need to visualize it. But yeah, now that I type it this way, it actually generates the correct graph. Okay, cool. So for the first part, if I can still remember what I did before I slept, essentially what we did was we calculated at every single point the x and the y's, and we just checked what's the largest possible rectangle, assuming both of them can be pairs. So for the second bit, it is slightly different. So the second bit requires us to generate these green tiles all around, and store them. My initial suspicion here is that we would generate way too many green tiles to store in memory, because I'm just assuming that the data set is just large enough that it's just impossible to fully store it in memory. But if we do want to do that, I think we can do something similar. So let me just do a print grid function so that I can let's see, this is the red tiles. Yeah, so I am just going to do yeah, and then let's just do red tile set. Okay, so let's not care too much about this. We first of all care about two things. So we want to zip all of your points with your neighbor, and we just want to generate the line directly, right? So if we just brute force this, you can actually see here, this is ax, ay, and let's see, oops, and bx, by, right? So you have ax and ay, bx and by. And we essentially want to generate all of the possible points in between the two of them. And those possible points in between the two of them will be the green tiles. So essentially what we want to do is for x in the range of ax. So ax actually starts with the original, so we want to skip the first, and bx is the one that ends at the original, ends at the new, which we also want to skip, so we just do this. So for every of these ax and bx, and then for every y in the range of ay to by, we can say that the green tiles x and y, right? So so let's see what's up with this. I see. So we need to define the correct start and the end. Start would be the minimum of ax plus 1 and bx. So we can say start x, end x is the max between these two. And in the same fashion, we can actually do this for the y's. So we actually do start x to end x, start y to end y. Okay, cool. Let me just try to visualize this as well so that I have everything. So we have the green tiles, list of RC coordinates. The green tiles were never exceeded, so we can use the red tiles as my maximum ranges, that's fine. If the x and y belongs in the green tiles set, right? So let me just replace this with a green tile set. We can do this. And then we can just try to print. We can try to print out the grid with the red tiles, which is the data, and the green tiles, which is the so the green tiles doesn't really need to be a set of this, it can just be a set at the beginning. So we can just do something like this. Okay, cool. Yeah, so you can kind of see here now we have actually drawn the correct grid, basically, right? If I am just to write it out on the entire output, yeah, you can kind of see here that I think even if I shrunk my terminal, it is way too many points, because I'm assuming that the grid essentially starts and stops at a very certain position, and it doesn't actually need to doesn't actually populate everything. So I think storing it is basically not a very wise approach for us. But I think it is possible to still store it. I think this takes a while, but it does generate in about a second how many green tiles there are. So that's one. I'm thinking if I'm thinking if it is possible for us to use the same behavior as before, where essentially we can treat them all as ranges along the graph. So sorry, let me just check my phone for a bit. Right? So rather than thinking of this as a strict set of points, because then we have to check with if a certain set of points exists within the other, I think it's easier if we think of them all as ranges of the numbers, right? So the column range has one range, the column has one range, the top has one range, the left has one range, the right has one, everything has one range. And so when you attempt to perform, or when you attempt to create a range between these two points, you create additional ranges, and all we have to do is to check that the new range that we generate falls within the range of an existing pre-existing line, and if it exists within a pre-existing line, then we know that the range actually works for us. Yeah, I think that's like a more intuitive way for us to approach this. So you can think of this as the tile lines, right? And what we do here is that we say that the tile lines basically has to do the start x, end x, start y, end y. Yeah, and then if we just generate this, you can see it's a lot faster, but it also tells me the lines in which the tiles will start and end, which is sort of what we want, right? Where we are now aware of, actually it's these two, sorry. Yeah, where you can kind of see here, maybe let me run this on the test example. You can kind of see here that we're essentially saying, okay, there is a line that exists from 7 to 11 from 1 to 1, right? And then there's another line that exists from 11 to 11, 1 to 7, and all of those different coordinates. And the reason why I say this is because now, if we try to do use the same algorithm as before, where we attempt to go through all of the lines in the data, so we try all of the multiple points as well, we don't just care about the width, we care about other factors as well. So the first thing we care about is we want to figure out the lines. So we can say that the top line between two different points is essentially the x coordinate of one to the x coordinate of the other, along with the y coordinate of one to the y coordinate of the other, right? Someone's asking me. Yeah, so basically with these 2 points that we have chosen, we want to determine the top line, the left line, the right line, and the bottom line. So the top line is comprised primarily of the y value. So it's the minimum between, so you can say the top start is the minimum between the y values and the top end is the maximum between these y values. Right, so let's just see what that looks like. So you can kind of see here, the very first line between the 2 points would be 1 to 1, but then some of the points is 1 to 7, some of the points is 1 to 5. Cool, and then you can have the bottom start. So for the very lowest point, that is essentially looking at the oh no, sorry. Yeah, so you have the top being the minimum of these 2 coordinates. You have the bottom being the maximum of these 2 coordinates. You have the left being the minimum of the x coordinate. And you have the right being the maximum of between the right coordinates. Bottom, left, right. So you can kind of see here now. Yeah, so you can kind of see here that for each and every one of these boxes that we generate, we actually generate from top to bottom, from left to right, and these are some of the coordinates that we take into account for, right? So yeah, so this is essentially the ranges of my numbers that we can operate with. And now, if we can think of these as the arbitrary lines of the box, we now need to make sure that all four edges of this box fit within all of the possible tile lines, right? Because then that guarantees us that we can find it. So I guess here we don't actually need to care about this. We can actually literally just say the width is the left, right minus the left plus 1, and then for this it would be the bottom minus the top, and then that would be the solution. Yeah, because if we just run it normally, it works as per normal. Okay, so let's just say that top fits would be any for every interval in so for any of the interval, for any of the I guess the line. So the line has the start x, end x, start y, end y. For tile lines where the tile line would accommodate for this particular top. Yeah, so essentially what we want is we know the coordinate for this top level, which is the y-axis. So we need to ensure that the top stays within the start of y, end of y, right? And then yeah, so essentially this is what we know if the top can fit. We basically say the top is between the start of y and the end of y. So for every possible tile line that can basically get arranged in this way, it has to fit within this particular range. And we also then need to make sure that the okay, give me a second. Let me go and get a laptop. Get my notebook for this to draw. I am back. I got my notebook so that I can draw this out because this is very confusing for me as well. I'm usually not too good at visualizing all of these things. But yeah, so you can essentially imagine that we have a couple of points, which are the red bricks, right? And we essentially draw lines between the two of them, right? And we connect all of them together, and these form the boundaries in which the rectangles can form. And what we want to do is, if I pick two different points between the grid, they themselves would also form their own lines. So yeah, so I don't know if you can see it here, but maybe it's a bit difficult. But essentially, suppose the solid lines are the lines that are the tile lines. We will also inevitably have 2 points that we've picked, for example, this lower point and this higher point, where we draw additional intervals as well. And what we are interested in this scenario is to make sure that the interval lines exist within an existing tile line. And as long as it exists within the existing tile line, we would treat it as a good thing. Yeah. That is essentially it for the high level idea, I guess. Let me turn on the air conditioner. But yeah, basically, we are now at the step where we want to generate these lines. So I know what the top is, I know what the bottom is, I know what the left is, and I know what the right is. Right? So I know the boundaries of my box. So let's generate these numbers first. So let's say, so we have the top line, and if you're following the same structure of start x, start end x, and whatever, the start x would be the left, end x would be the right, the start y would be the top, end y would be the bottom. We can have the bottom line would be sorry, it would be the top and the top. This would be the bottom and the bottom. The left line and the right line. Right? So we have now the lines that the new box would draw. And essentially what we want to do is we want to say for the top line, for example, this top line needs to fit perfectly within the any of an existing tile line. And if it does, we found an answer. So to identify this, it's essentially saying the end yeah, so suppose we have a tile line that goes from A to B and then X to X because it's a horizontal line, and the top line is A to C, X and X. Well, we make sure that the start y and end y is the same, so we know we are on a horizontal line, and for the fact that the primary line needs to be smaller, so the left has to be greater than or equals to the start x, and the end has to be less than or equals to the end x. Right? So in this scenario here, we are saying that this is the left and this is the right. Right? Because we've kind of expanded out what this number looks like to us. And in the same fashion here, we can say that the bottom fits. And so what we are interested in is making sure it's a horizontal line again, so we can say bottom. But we need to also make sure that the left and the right also fit, which is what we have done. We can do the same thing for left. The left. So for a left coordinate in particular, the tile line will look a bit different. So suppose now, for a left side, for a left wall, the x coordinate remains the same, which is the x. So it would be, say, for example, x and x, but now a and b becomes the other variable. And so you have x and x, a and c, for instance. And so we kind of have to flip this a bit, where we say that it starts on the left, ends on the same left, and the start y is smaller, so the start y is the one that it's a higher point. So we need to make sure that the top line is greater than or equals to the start y, and the bottom is less than or equals to the end y. Okay, cool. And so we can say left, right, and the same logic would apply. So we can say if top fits, bottom fits, left fits, right fits, then we go ahead and calculate the potential answer. This does not look correct at all. But now it says it's 24. Let's just do left, top, right, bottom. Yeah. I don't even think this would be fast. Yeah, it's not fast at all. Yeah, I'm trying to think of ways we could do this. I don't think this is the right way, also because it's not the correct way at all. Because it produced 8, even though it should not produce 8. It should have been... Yeah. Okay, let me just close down this window so I have a bit more space. Yeah, I'm trying to think of the best way we can solve this. I think regardless, we kind of have the correct idea where we treat each of these as just pure lines, and we just want to make sure that they fit at a certain line. I guess one way we could try to simplify this a bit is, instead of treating it as tile lines, we can just say vertical tile lines, horizontal tile lines. We can say that if the start x is the same as the end x, this means it's a vertical line. So the vertical tile lines, we want to index it based on the x coordinate. I guess we will just import the default dictionary for now. So we will say that this is the default dictionary of list and the default dictionary of a list. So we want to append the start and end y instead, right? And so in this else, this would be a horizontal line. Horizontal. Okay, cool. So we, instead of caring about this, we actually care about the individual lines itself. So let me just maybe comment these out first. So we have vertical tile lines and we have horizontal tile lines. Yeah, so you can kind of see here that we say, okay, for a rectangle, or for one of the tile lines, if you are bound on the maybe let me just print out the graph as well. Print grid. Let's pass it the data. It's an empty set because I don't want to generate everything. Yeah, so you can kind of see here, we are claiming that for the vertical lines, we exist in several coordinates. So you have a position of 11. So 11 goes from 1 to 7, which is the rightmost you see here. There is also 9, where it goes from 5 to 7. There is 2, which goes from 3 to 5. And there is 7, which goes to 1 to 3. So those are all of the vertical lines that are formed. And then for the horizontal lines, we have things like 7 to 11 at the 1. We have things like 9 to 11 at the bottom. And then we have 5. And then you have 3. Okay. And then what we want to do afterwards with all of these like coordinate of lines is we want to do something similar to what we did previously, where we say we know the top bottom, left and right lines. Top to bottom is one set. Is one set. Left to right is one set. Yeah, you can kind of see that these are all the possible lines we can try to draw. And then we can kind of, imagine this as a, suppose now, I want to make sure that the top to bottom line, so this vertical line, is valid. We would simply check against the left and the left and the right to make sure that it exists, right? So let's just do the top to bottom line, right? So what we want to do is we want to check both on the left and on the right that there exists tile lines that fit this particular range, right? So for every, let's see, tile line in the vertical tile lines, and let's say at the left position, any left fit, right? We can say that the any left fit is equal to whether or not for this given end, for the current top to bottom, it fits, which means that the top has to be greater than or equals to the start, and the end has to be less than or equals, and the bottom has to be less than or equals to the end. If any of the lefts fit, let's break, right? And then we can say left becomes right, and we would say that the same property applies, and so the top fits if both the left fit and the right fit, right? That would be the first priority that we give, right? That's what we would say. Yeah, and so what we can essentially boil this down to is we can say that the top fits if any for the start and end in the vertical lines at the left, where the top is greater than or equals to the start and the bottom is less than or equals to the end, and yeah, so essentially the top fit is just these two criterias, right? And then we don't have to do the top to bottom, bottom to top is the same. So we now want to make sure that the left to right also makes sense. So we can say top to bottom fits, left to right fits. So this is slightly different, where instead of the vertical, we change these to the we are changing these to the horizontal, and we would start again with the top position, where the left has to be greater than or equals to the start and the right has to be less than or equals to the end. And then this would be the bottom, right? So we kind of skip over these few, and we just check if at any point of time the top to bottom fits and the left to right fits. It still prints 8, which is clearly not what we want. So yeah, so maybe let's pick up the points between 9 and 5. So if data of I let's just say that we picked what is the order in which the data points come in? 9 and 5 and then 2 and 3. So let's pick 9 and 5 and 2 and 3 in that order. So if the data points come in 9 and 5, and data of j is 2 and 3, hi, top, bottom, left and right, and let's print out the outcome of the above checks. So top to bottom fits, left to right fits. Okay, yeah, so for some reason it just doesn't fit. I'm not entirely sure why either, but let me just stop printing a bunch of our data so that I have cleaner outputs. Okay, cool. So essentially, if we have these lines, we claim that the top to bottom, which is the y-axis, is 3 to 5, which is correct, and then it's 2 to 9, which is also correct. So both are false, but why are they false? Right, so let's print out the vertical tiles, let's print out the horizontal tiles, and let's see. So in the instance where it's 3 to 5, we have a line. Okay, so when we check for the top and bottom, top to bottom, sorry, we check on the left side. So we are interested in the vertical, which is this one. Oh, we don't have any entries, which is why it fails. Hold on. Did I mess up the logic? Yeah. So for the vertical, why did it not generate? Yeah, so we say that the vertical tiles on the left, which happens to be 2, so we found 3 to 5, which means it fit. And then on the right side, the number is 9, which is 5 to 7, and 5 to 7 doesn't fit, right? So let me just check to make sure that this actually is correct. I see. It's because some of these lines have larger intervals than what we actually expected. Okay, so this might actually be a mini merge interval problem as well, where we do need to actually account for whether or not the intervals we are seeing is actually a full interval or a partial interval, and then we combine them. Yeah, I think that is the primary issue here, because you can kind of see, or you can kind of notice that that when we generate these points, essentially, we don't account for the fact that there could be an interval between these two additional points. Okay, this is a pretty silly problem, I guess. So I'm trying to think of a way we can generate all of these. So essentially here, we can just think of the entire shape as just a bunch of either vertical or horizontal lines. And what we are primarily interested in is to make sure that we capture fully what these vertical and horizontal lines are. Yeah, I think that's like the primary focus that we have. So what we want to do in this instance here is we don't just care about between these 2 points, but we also care about, say, between points of the same height, right? Do they form, like, what other lines do they form? Because these will always be formed by points along the same height, or even or even just like basically just points along the same height, right? You would eventually intersect between multiple lines. Cool. So let me try to think of what we could do to capture this in our answer matrix to make sure that we are actually getting the correct answer now. Surely there is some kind of geometry, mathematical computer graphics way for us to solve it. But I don't have that background, so unfortunately I will have to come up with it myself, which is okay as well. But essentially, ooh, maybe not actually. Maybe not. I'm running out of battery as well, which is not a good thing, so I might have to charge my laptop and come back again. But I am wondering, maybe, just maybe, we can use the odd even rule again, where instead of trying to see if the lines fit and trying to generate all of these lines, we instead think of it as, does the left point exist within the current polygon? Because right now we are basically generating a polygon, right? It's just a shape. If a point is, for example, here, and we basically we burrow down in a certain direction, and we realize that it intersects across two exterior lines, it means that it's outside. But if it exists within the polygon or on the polygon, it should actually intersect. Oh, sorry, wait, let me see. If we burrowed down this way, it would be 1 point of entry, 2 points of entry. But if we instead we had one here, it would be 1 point of entry, 2 points of entry. I think the trick here is actually the odd even rule. In computer graphics. Yeah, I think it's this rule actually, the even odd rule, where we basically form a polygon and we use the and we check if it belongs on a path or a boundary. And I think what it essentially says is so we essentially cast the ray from the point to an infinity in any direction, and the number of path segments from this given shape. So if this number is an odd number, it would be inside. If it's an even number, it's outside. So if you look at, like, let's say a point here, and let's suppose we just draw the line downwards, we only exit from 1 point. Same thing if we draw it if it is along a corner, it doesn't really matter. What matters is if it crosses, right? Yeah, so you can kind of see here that is the way we check it. I think in the same way, we can also do it horizontally, we can do it diagonally, we can do it vertically. But essentially what we want to do is we want to make sure that the left, right, bottom, and top all exist within or on the polygon itself. And if we can find it to exist within or on the polygon, and all points exist within or on the polygon, that's a valid answer as well. Cool. So that might actually be the trick for us here. So let's see. Cool. So maybe we are not as interested in this anymore. Okay, let's suppose. So what do we require from this? We essentially require, again, I don't think I can remember it off the top of my head, so I will just kind of cheat a little about this. But yeah, essentially what we have here is the polygon, which is the list of the tuples, which is basically the lines that we have been given already. And so what they are essentially doing here is they are going through all of the possible lines within this polygon, or I guess all of the possible pairs within this polygon. And what we are saying is, if we have encountered a corner, which means that a given point exists along a corner, it is in, right? Because it has to be, it has to have intersected between two different lines. It exists on the corner. That's fine. The alternative is if the the AY is greater than the BY, AY is greater than the Y, and it's not the same as BY is greater than Y, which means that it is a slope. We will perform the operation here. So yeah, I'm not entirely sure why it says a partial example definition, but maybe let's just assume that it is right, for now. Yeah, basically. So for the point that we are given, we want to search for it, right? So let's just say that we have in lines, or in polygon, I guess, self. So we are given the x, we are given the y, and we are given the lines, which would be the list of the xy coordinates. We return a boolean for this. And so it's saying for I in this range of the length of these lines, right, ax, ay is equals to the lines of this, bx, by is the lines of I minus 1. So if it's at the very beginning, we actually overlap to check for the previous one. We check if ax happens to be x and I think ay is y. This is true because this exists on a corner. We can return C from this. And then what they do is they say if it's not equals to the by greater than y, which means that for the given y coordinate, it's on kind of two different points, I guess. The slope would exist as times by minus ay minus bx minus ax times y minus ay according to this. If the slope happens to be equal to 0, this is exists on a boundary. Yeah, cool. And so essentially what I want to say is we want to say we need to just keep track of the tops and bottoms. So if the we can say I'm running out really low on battery, so I'm going to pause the recording and I'll come back. Hey, so I am recording the explanation for day 9 for Advent of Code 2025 now. I know it's a day late, but I basically was really tired yesterday, so I didn't have the time or the capacity to try to solve it. But yeah, so for day 9, I think, just to recap, it's raining really heavily now. So for day 9, to recap, the first part was super simple. Basically, they just wanted us to pick 2 points, calculate the size of the area, and see if it, see which was the largest. So that's basically a brute force enabled solution. The one that took a bit more time to grok was actually the second part, and I think maybe I'll include it in the rest of my recordings, but I did come pretty close in figuring out most of the solution, where I had both bits of the solution just not together at once. So maybe I'll just quickly summarize. So essentially for the second part, the question is asking us to bound each of the rectangles we form to within the polygon of the shape that we're creating. And the reason why this is difficult is because if we just try to brute force all of the sizes, we don't know what's considered inside unless we populate all of the values within the polygon and check it directly. So that I think that's one of the other solutions I've seen, which is basically flood filling the whole polygon shape and then checking if the values are present. But that isn't as ideal as what we want. So, well, that is possible. I just didn't really manage to come up with the solution for that way. So I kind of worked on it in a different way. So the way I chose to solve this, I think, was kind of combining two bits of what we already thought about previously. So there were two sort of ideas that I had previously, which is the first idea is every rectangle, each edge or each line of the rectangle, each edge of the rectangle has to fall squarely within any of the existing edges of the polygon. So if an edge exists, or if a particular line exists on top of an edge, it has to be within the edge itself, because otherwise if it exceeds, we know for sure it's out of the range. The second kind of thing is for every corner of this new rectangle, it also has to exist within the polygon or on the polygon. And for us, so like kind of the ideal solution is taking these two and combining them together. So we ensure that all of the corners exist on the polygon or within the polygon, and we also ensure that every line of this rectangle exists well within the available lines of the polygon itself. And there is a caveat here, which is that I think there has been some posts on the Advent of Code Reddit subreddit where people have found that there are certain inputs that break many of these solvers, including mine, because mine can't manage to fix for that. But basically, if you were to print out this entire solution, you actually realize that it's basically a sort of like a circle or a circle with a bit of an indent. And so because of the specific type of solution shape, this particular solver works, but there are certain cases where the shape just looks a bit different and now it breaks the entire way we check it. And so because of that, I didn't really spend as much time trying to solve and fix my edge cases for that. But I will just briefly explain what I am doing currently and why it works for the current solution that we have in this case, or current problem we have in this case. And then I will maybe link additional resources for how do you solve the other parts. Cool. So essentially for part 2, there is a bit of preparation steps you have to do. I guess the main preparation step is to actually isolate the vertical and horizontal lines, because we're connecting basically from point to point, it is always going to be vertical and horizontal. So we want to basically deconstruct the vertical and horizontal lines separately, and we'll get to why we do that in a bit. But essentially now we have two different sets or two different arrays, one for all of the vertical lines, one for all of the horizontal lines. And then the intuition here is we try every possible rectangle again, and we check if that rectangle is valid, and if it's valid, we can override the area. There is a bit of an optimization we've chosen to do, which is to basically check. We calculate the area beforehand, and we check if the current area that we are looking at is larger than the answer, and if it's not larger than the answer, there is no need to even check if it's valid, so we just skip over it. So that kind of cuts down a bit of the searching, but not by I don't think by a very significant amount where it actually matters for us. But I might be wrong, but yeah. And so the next interesting bit here is actually looking at how we check if a rectangle is valid. So we do very similar calculations as we did before. So we essentially calculate the points on the top left, top right, bottom left, bottom right. I think in the previous clip I was actually naming them as top, bottom, and left and right, and I think that was really confusing. So I just decided to name them the minimum of the x, the minimum of the y, the max of the x, max of the y. And for all of the given corners, which is basically the x and the y's combined together, we can check if the corner is either a red tile, which means that we know for certain it's in, or if it is on the within the polygon itself. So the way we check whether it's within the polygon, it's actually a pretty simple algorithm. I think I wrote a pretty complicated algorithm by copying from Wikipedia, but actually the algorithm is super simple. The idea is we go through all of the possible vertical lines that we have. So you can see here I'm passing in the vertical lines. So we go through all the possible vertical lines, and for every line that falls within the the y range. So I'm kind of drawing this point to the left, if it is possible. Sorry, no, I'm drawing this point to the right. So if a particular point is moving to the right, and we encounter a point or a line that is there is next to it, or that's to the right of it, and it exists within a particular within the y range of the line, we would basically keep flipping this inside. And so for every even number, it is not inside. For every odd number, it will be inside. So that tells us if the point is within the polygon. But this check alone isn't sufficient. So what we want to do next is to then perform the operation where we check against every single possible horizontal and vertical line to just check and ensure that for each of these lines that we have drawn, whether or not we are well within any possible edges of the polygon. So if it's not well within the edges of the polygon, we know it's also not possible for the rectangle. So by doing these sort of these three sets of checks, we essentially help us determine which are the available rectangles that we can find. So that's the main solution, or the main intuition behind the solution. It's actually relatively straightforward once you've written it out and thought about it. The main problem here is there's a lot of boundary conditions. It's very long and tedious to come up with this solution itself. But I do think this was a pretty interesting problem overall. I was pretty happy. I thought of the idea of the two discrete solutions, but I just didn't manage to combine them in time yesterday. But yeah, I think overall this was a pretty interesting day for day 9, and yeah, I have day 10 already loading in the in iMovie, so it's being prepared. But today will be a pretty much like a tool upload kind of deal. So thank you all. See you all, I guess, day 11. See you.